Hello, welcome back to my channel. This is Supercomputer Nepal, and today I will be showing how we can install Quantum Espresso using CUDA library and compilers as well as MPI library so that it can run in massively parallel mode. So I am logged in a supercomputer here, and I have already downloaded the Quantum Espresso package 7.2. Let me go inside, and as usual we have configure script here. Okay, so right here is the configure script, but the difference this time is that we require some special flags to pass while we configure the package. So let me show you what are those flags, and I have written that in a CUDA.txt file. By the way, now I am going to conduct a CUDA session further, and then I will cover the MPI session. So the thing is here, this is comment line, /configure, and with CUDA is equal to nvhpc. It is a variable as it starts with $, and CUDA compute capability of this Titan V card is 70, so it is the value. And CUDA runtime, I am using 11.2 version of CUDA, so this is what I have defined here. And I am disabling parallel because GPU version is if you have only one GPU, then this is what we do. And enable openmp, and scalapack is equal to no because we don't need parallelization here. And this is the prefix, that means where we will be installing, but for now I will not do that. Let me copy, by the way, while I am here in this file, but only up to the scalapack is equal to no. Okay, so right here I am doing this, and I close the file. So now while in a supercomputer we have HPC SDK already installed, and as a module, let me show you. Module AV will show you the available module, and I am particularly using this one, which is without parallel, no MPI, and the nvhpc version is 21.1. okay, that's it. I all need is this one module. So I will be loading that module by the command module load, and the name of the this is my mistake, sorry for this. nvhpc nompi no MPI /21.1. so module load and the name of the module. Okay, this is how we can load the module, and we can check as well. Module list command will show you the loaded module right here. So that's it, I am done. Now I have to do is configure it. Okay, so this configuration is particularly for the Titan V card or any similar card whose compute capability is 70, and particularly for this compiler, this is the 11.2 version of CUDA. So I am defined is here that. So let's hit the enter. It doesn't take much time, it will be done very quickly. So it's done. Okay, there is no error, and you can check this message, configured for compilation of serial execution, because I disable the parallel in the configure flag. Okay, so it will recognize the library and LAPACK plus, and FFT is not detected because it is not in this particular version. Okay, as not well directed here, so no problem. Now I am done. Let's do only PW compilation. It is same like previous one. Make PW, and if you want to compile faster, because I have more cores here, so I can do -J4. Make PW space -J4, and it will be compiling using 4 CUDA cores, so it might take little while. So far compilation has been finished. Let me go to bin folder and see if I have the binary file of pw. Yes. So this is how you can continue other parts of Quantum Espresso such as phonemes. For that you can continue make pw all and minus j4 and it will populate all the packages. Okay. So but right now I will be going back to the parallel compilation using openmpi in this case, and very similarly you can use parallel compilation of Quantum Espresso using Intel OneAPI also. They are almost similar, and particularly I have compiled this 7.2 already, and but I will show you what to do for that. If you want to do that, let me show you exactly what we have to do is like this. Go to the website openmpi.org. I will keep this link on the description of this video, and this is the front page of that, and you can hit the download button right here, download, and then you can choose one of the stable, but for this particular purpose I am not using. Mine is I think 4.1.2 version of this one because I compiled this library little ahead. Okay, but you can do any one, the earliest one, and we can download this package. Let me show you. So you can copy the link and then minimize your browser and go to here, and you can download that package. It might take a little while. Let me see. Yeah, download is done very fast. Okay, the package is right here. Okay, you can enter this package by tar minus zxvf nvhen mpi, and then you can just go inside that openmpi, and it is very similar to the Quantum Espresso and Fourier transform compilation. There is a configure script, so you can do configure, and you can do prefix, means where you want to install the OpenMPI library. Okay, so but I am not compiling it right now, but I will use this as a module because I am already in the supercomputing environment. Let me show you module AV. Again you will see that OpenMPI is somewhere here. Yes, this is the module that I require for parallel installation of Quantum Espresso. Not only this, but I need this library as well, this compiler, GNU compiler. By this compiler I am compiling this library earlier while building this module. Okay, so I have to load both these GNU 9 and then OpenMPI. So this is what we have to do. And by the way, I can remove earlierly loaded CUDA compiler, nvhpc compiler. So what I can do is module purge. Module purge will remove all the modules from here. So let me check that module list, and it should not show me any module, which is correct here. So now currently no module loaded. Now I will load the two modules. Module load GNU 9. So this is one module, and in the similarly I can open MPI 4.1.2. So let me do module list, and it will show you these two modules. Okay. Okay, now I have the required module. Then I will go to the Quantum Espresso folder again, cd QE folder, and I can do dist clean, which I might have already compiled using CUDA. So in order to make a fresh, then do this make dist clean. It will clean all the previously compiled things. So what I am doing now is using the again configure script, configure, and this time I will enable the parallel. So the flag is like this, enable, but I still disable the openmp. Okay. And then if I want, I can write the prefix. That means where I am installing it. Okay, but I will not do this right now. Let it be like this. The flags are here. Okay, I will keep these flags as a well documented in the video in some time later. If not right now, right today, but I will update in the later period of time. Okay. So now let me configure with a parallel mode. And here what happened is that parallel environment detected successfully. So this is the main message I am looking here. The configured for compilation of parallel executables. If you see these two lines, that means you are compiling it in a parallel mode. But before that, I might be missing something here. Okay, particularly the with-scalapack and Fourier transform library, which I have actually here in my system. Let me show you module AB. Then I will compile in a more better way. Fourier transform is here. Let me load this module. So I loaded Fourier module, and next is scalapack blast library, which I should have somewhere here. Yes, I have. Yes, let me load that library also. These two libraries. Now let me see what are the libraries currently loaded. Module list will show you these things. So I have GNU compiler, OpenMPI parallel library, Fourier transform, and scalapack blast library. Okay, so I will do the same thing, same compilation now. Enable parallel, disable OpenMP. This time it should detect blast, scalapack, and Fourier transform. Okay, let's see. Yes, correctly. So blast library is here, scalapack library is here, and Fourier transform is also detected, and parallel compilation is also performed. So typically I am done. So this is the main thing I would like to convey in this tutorial video. So, and after that I will be showing some benchmark result, which will be the very important part of this video. And I have done, however, parallel compilation using OneAPI, Intel's compiler here. Let me go to my Github page first and show you the results there. You can also follow this Github page. This is my Github page. You can click the repositories here, and Quantum Espresso benchmark folder is at the top, and possibly I might be putting it on a bookmark first page as well later on, right now which is not. So there is I have kept some Slalom file for the job submission in supercomputing environment, although it could be different. Okay, in your environment it may not be fit right away, but it is a good guide. However, I am not claiming this will work right away, but it's a good guide to work. And there is a PWSCF calculation input file for Quantum Espresso, and I am using phonon benchmarking input file also. In fact, these two files are very heavy files, like 16, 16, 16 k-point grid, and reasonably large cutoff energy as well, kinetic energy cutoff, and others are as such. And let me show you phonon. Phonons are phonon spectrum, there are 4 by 4 by 4 Q point grid is implemented, and threshold of convergence is 10 to the power minus 14. And this example is for silicon, and all the output file are here. You can see all the output file here. Just for example, ph_cpu.out represents the single core CPU serial calculation of phonon, and ph_gpu is the multi-core, that means multi-threading in a GPU Titan V, which is a award from NVIDIA to me. And another is MPI, that means a parallel but without GPU in a AMD thread Ryzen Threadripper Pro CPU. And I have here a readme file as well. You can check other things. And the important is I will show you the bookmark result without further talking. Time.txt is the bookmark timing here I have done. So the first top 5 lines are for PWSCF calculation, and bottom lines are the phonon calculation. There is a huge difference. Let me show you. Basically, let's see that wall time to understand. The SCF wall time for one core is in a Threadripper Pro is 2 minutes 16 seconds or 17 seconds, and in parallel this is just a half. And what it shows is the PW calculations are typically not that much scaled in comparison to the phonon calculation, okay, because phonon is taking long time. So, and I have shown this thing almost 24 hours in a single core CPU of the same processor, and in MPI 4.5 hours is taking, like a huge difference in MPI. And GPU in Titan V, this run is done. Titan V, it is taking almost 5 hours to run the phonon calculation, and there is one more calculation is performed in RTX 6000 card, Quadro RTX 6000, which is also an award to me by NVIDIA, and it is around 8 hours. PW calculations is as a ratio, they looks good, however. So in comparison to single core and GPU, the time is, or parallel, phonon calculation is very much faster actually, both in MPI or GPU. And GPU, it is slightly slower than 16 core. Let me see. And in RTX 6000 card is particularly for the single precision calculation, so time is still higher for this card with a typically similar environment. And so this is it, and I will be keeping other videos. So I want to request our viewers of this channel, the Supercomputer Nepal, if you like to donate latest brand of batch of GPUs, especially the A100 or H100 type of cards, you are more than welcome to contact me, and how we can use those donations in favor of yourself and in our research and training purpose as well to the students and all over the old Nepal, everywhere. So you are highly welcome to donate those cards if you can. And as a reciprocity, obviously I will be promoting your business as well as, and we can do some benchmarking results that will be useful for the many different scientific and engineering communities as well. And that's it for today. I would like to thank you very much for your time, and please do subscribe the channel for encourage me to make these videos more better and diverse and more useful. Thank you very much.